Right, so the geometrical representation of complex numbers, which we've already seen, of course, we can represent as a point on the Argand diagram. Okay? So another way of describing them, and this is the beauty of mod arg form, is as a vector instead of a point. So instead of a point, describing it as a line or an interval. Okay? So here's our Argand diagram, and there's our random points. Now, its position, and there's only one position the single point can go, is at x, y. And I can't move it. It's got to stay there. So I can't really do anything with it. But if I make it a vector, I can now move it. Because the length of that vector, the modulus, and the angle it makes with the horizontal, as long as all I'm doing is sliding and things like that, will always stay the same. It doesn't matter where I put the vector. And so then that has a huge advantage when it comes to adding and things like that. See, if I put it down there, it's still got the same length. It's still making the same angle. I can put it over there. It's still got the same length. The question is, how do I work out which complex number it represents? And you always go head minus tail. So when it joins up to the point that represents the complex number, then it's easy because I could say, oh, well, z minus naught. And so you got the same answer. Whereas when I move it over here, it would be some complex number minus another one, but the answer to that would be x plus iy. So it's all head minus tail tells you what vector the complex number represents. So no matter where we put it, they're going to stay the same. Okay, so yes, I say head minus tail, head minus tail. So all right, how do we add and subtract? There's z1. Represented by my red vector there. Z2 represented by the blue vector. And all we do is translate the vector. And we place the tail of the one we're adding on the head of the other one. So head to tail, we call it. So I just slide it. And so the head of Z1 and the tail of Z2, it's like we're adding them. We're going, okay, I'm going up Z1 and I'm adding Z2. The new vector, green, is the answer. And of course, it's joined to naught. So whatever position that is, that would be Z1 plus Z2, the answer. And the beautiful thing is, if you look at it, because remember, you can add numbers. You don't have to go A plus B, you can go B plus A. And this still works. Because if instead of doing it that way, I'd said, no, let's slide the red one and put it on the blue one, I still end up at the same point. So it preserves that idea of adding. You can add in either way, A plus B or B plus A. To subtract, then instead of going head to tail, you go head to head. So it's like adding the negative vector. So to find, there we go, that one there would be Z1 minus Z2. Because I've slid it, but instead of putting in the tail of Z2 on the head of Z1, I put the head on it. So it's gone head to head rather than head to tail. Or another way of thinking about it, if I go Z2 minus 0, I get Z2. But if I read the vector the other way, I go 0 minus Z2, I get minus Z2. And so this is now the tail of minus Z2. This is now the head of minus Z2, and I'm just adding them by sliding it across. And of course, when you add a negative, it's the same as subtracting. And there's the black vector that would represent Z1 minus Z2. But here's the beautiful thing. Again, it's all preserved in the picture. I could slide that black vector somewhere else and it would fit perfectly. Can you see where it is? Yeah. It's the other diagonal. There. And that makes sense. Because remember, head minus tail. I could go Z1 minus Z2. If I was to slide that to the origin, there it is, Z1 minus Z2. Okay. So when we create this, what we call the parallelogram, I think in physics they actually call it the parallelogram of forces. But that's all right, we don't need to know that. I mean, that's a physics thing. But the two diagonals in that parallelogram, one will always be Z1 plus Z2, and the other will be Z1 minus Z2. It could also be Z2 minus Z1. It just depends how you're reading it. So I could have gone Z2 minus Z1 or Z1 minus Z2. still has the same length. The thing that's changing, of course, is the angle, because you always measure the angle at the tail. So if I'm going Z2 minus Z1, Z1 is the tail, my angle would be that obtuse angle in there. But if I was going Z1 minus Z2, then the angle would be a negative acute angle. Okay. This thing called the triangular inequality. It's kind of obvious if you think about it. If you've got a triangle, any side is going to be shorter than the sum of the other two sides. Because the shortest distance between any 2 points is a straight line. So if you think about it as a path that you're walking along, if I want to get between 2 points, the quickest way is to go straight there. If I decide to deviate off and then go back to the other point, obviously I've travelled further. That's called the triangle inequality. So if I look at it in triangle ABC, and what would have been really good is if I labelled A, B and C there. But use your imagination. There's a triangle ABC there. Then the length of AC, which would be one of those sides that we can see there, it's going to be less than the sum of the other two sides, AB and BC. The equality, because it's less than or equal to, would be if AC was a straight line. Because then B would just be somewhere in between A and C if it was a straight line, so that they'd be the same. But the reason that's useful is for this. Because I can now say, if you look, and the triangle I'm looking at is the green vector, the red vector, and the blue vector. And I know the lengths of those. The red one would be the modulus of Z1. The blue one would be the modulus of Z2. The green one is the modulus of Z1 plus Z2. And so that's a way of proving that the modulus of Z1 plus Z2 will always be less than or equal to the modulus of Z1 plus the modulus of Z2. And if we had to prove that, all we had to do would be draw that triangle, and we could say, well, by the triangular inequality, that that's true. So, okay, let's have a little bit more look at, about addition. So there's our parallelogram that we just saw, but drawn freehand. So addition, as I say, is when we add them, we'll end up at that third point there, Z1 plus Z2. Subtraction is when we slide it and put the tail there. Note, AB is the modulus of Z2 minus Z1, or the length of the vector that joins A and B, because the vector that joins AB would be Z2 minus Z1, or Z1 minus Z2, depending on which way you're reading it. But its length would be the modulus, and the argument is, it's over in this diagram here, the argument is alpha, whatever angle it makes with that horizontal. Let's do a question. 1995. It's a good question, actually, for this. There they are. They've given us 2 points, P and Q. Thus, the length, they've given us a little bit of a hint there, because if P is the complex number Z, Q is the complex number W, then PQ would represent the complex number Z minus W or W minus Z, depending on which way you're reading it. But they're saying, well, thus the length of that would be the modulus of Z minus W. This is what I was just talking about with triangle inequality. So the first question, show that that length is less than the other two. So I need to explain it a bit, so I drew in my blue line. So in my exam booklet, I would have redrawn the diagram and draw in PQ. And I would have said, well, the length of OP is the modulus of Z. Length of OQ, modulus of W. They've told me the length of PQ is the modulus of Z minus W. And so then I'd say, well, there we go. Using the triangle inequality, we can say that this side of the triangle is going to be less than or equal to the sum of the other two sides of the triangle. All right, so we're now going to construct the point R representing Z plus W. And then they want to know what can be said about the quadrilateral. All right, so let's find R. There we go. Draw up our parallelogram. There's R. What can be said about the... I suppose we could say a lot of things. We could say, oh, gosh, it looks nice. Lovely use of colour. Don't think that's what they're looking for, though. I think they're looking for one key fact. What do you think it is they're looking for? What can you tell me about that quadrilateral? It's a parallelogram. I guess that's really what they're looking for there. Right? Has to be a parallelogram, remember? Because all we've done is slide the vectors, so they must be parallel to each other. Opposite sides are parallel. We have a parallelogram. So yes, OPRQ is a parallelogram. But then they made it even more interesting. Let's imagine that the length of the vector z minus w, so one diagonal, is equal to the length of the other diagonal. What can be said about w divided by z? If the diagonals are equal, we know it's a parallelogram, what can we now say the shape is? Anyone got an answer? You got an answer? A rectangle, fantastic. That's excellent. So we know, therefore, the shape is a rectangle. Very good. Now, if it is a rectangle, now we do know that the angles are 90 degrees. So look at the two vectors there, w and z. The difference between their arguments is the angle in that rectangle. Therefore, it must be 90 degrees. I've used radians, but the difference between the two must be pi on 2. But using our rule, remember, if we subtract arguments, it's like dividing. That's the same as the argument of w and z. So I now know the argument of w on z is pi on 2. What can be said about w on z? Its argument is pi on 2. What can you tell me? It's purely imaginary. Purely imaginary. So we didn't even have to know what they were. Just by playing with geometry, we could prove that, oh, okay, if I got w and divided by z, don't know what the numbers are, but I know I'll end up with a purely imaginary number. All right, multiplication. What happens with multiplication? We've seen this. This gives us a clue what to do with the vectors. We know the modulus of z1, z2 will be the modulus of z1 times the modulus of z2. So if I want to get one vector, multiply it by another, the length of the new vector will be the two lengths multiplied together. And with arguments, we saw we added the arguments. So that was that rotation idea. We rotate the vectors. All right. So what we're saying is, if we multiply these two complex numbers together, the modulus becomes r1 times r2. So the two moduli multiplied together. The argument becomes θ1 plus θ2. The two arguments added together. Oh, and remember that rotation is anti-clockwise. So we're going to get z1 and multiply it by cis theta. So the rotation will be theta, because I'm adding theta to the argument of z1. And you always rotate at the tail. Okay? So I'm rotating at the tail, and the length of the new vector has been multiplied by r1 in this case. So the length hasn't changed because I'm just multiplying by 1 cis theta. And cis theta there doesn't have a modulus in front of it. So the length of the vector hasn't changed in this case. But if it did have, if it was r cis theta, then we'd multiply the length by r, whatever that length was. Note, and this is the bit about multiplication by I. We know I is cos pi on 2 plus I sine pi on 2. So therefore, IZ1 rotates it 90 degrees. Length doesn't change because the modulus of I is 1. Its argument is pi on 2, and that's why we rotate it 90 degrees. So there it is. Multiplication by I, rotation anti-clockwise by pi on 2. We'll see that a lot, I think. Remember, a vector is head minus tail. Head minus tail. Let's play with this one. Here's a lovely shape I've drawn. And I've got 4 points there. A is W or omega. D is just the real number 1. Now, I'm going to get the vector DC. All right, so the vector DC. Oh, this is a square, by the way. The shape's a square. Forgot to mention that. Key bit of information. So the vector DC, if I wanted to work out what it was, because I know that's a square, I could say, well, it's the vector DA multiplied by I, because I've rotated it 90 degrees. That shape's a square. When you're writing a vector, there's your convention. The tail, see the arrow of the vector? So it's like the tail going to the head. So D is the tail. Well, let's work out what it is. DC. Well, the vector DC is not just one, it's head minus tail. So it's the point C, whatever complex number represented by that point, minus the point D, which I know is 1. And it will equal, okay, AD is head minus tail, so omega minus 1 times I. So from that, we can now work out what C is. We just got to manipulate this to make C the subject. So play around with it, and there it is. Depending on what omega is, of course. But there would be 1 minus I plus IW. Some people might rearrange it, but I don't know what omega is. So there's no real advantage of breaking up into real and imaginary, because if omega is imaginary anyway, it'll change the whole thing. So all right, let's now work out B. So to get to the point B, what I'm saying is, okay, I can start at the point A, and I'm going to add on the vector DC, because I could just slide that one up, and then I'd get to the point B. So I'm saying, well, the point B, I'll start at the point A, I'll add on the vector DC. Well, I know A is omega, DC is C minus 1. C we just worked out over there. So if I subtract the 1, add the omega, there's a value for B. That's one way I could have worked out B. Another way I could have done it is I said, oh, look, I'm going to start at the point C, add on the vector dA. I'd end up at the point B. Let's just show it does come up with the same thing. So C, that's 1 minus I plus I omega. dA was omega minus 1. Play around with that. Yeah, we come up with the same thing. There's another way I could have done it. I could have used rotation, because I know that this is a square. So I could say, I'm going to get the vector dA, and I'm going to rotate it 45 degrees. A square, so the diagonal must bisect so it's 45 degrees. So I'm going to multiply it by cis pi on 4, but the length of the vector will change, because if you think about a square, the sides and the diagonal are in the ratio 1 to the square root of 2. Because thinking of a 45-degree triangle, 1, 1, root 2. So I know the length of the vector would also be multiplied by root 2. So this should work as well. So dB, which is b minus 1, root 2 cis cos pi on 4 plus I sine pi on 4, times dA, which is w minus 1. Well, we know the exact values for cos pi on 4 and sine pi on 4. They're both 1 on root 2. So that'll cancel with the root 2. So I've got 1 plus I, w minus I, plus 1. Have we got it in the same format yet to prove they're the same? No, we just need to do a little bit of rearranging. And we come up with the same answer. So a different way of thinking about it. But the lovely thing is, it doesn't matter which way I do it, it works. That's the beauty of the vector. The geometry backs up everything we've been seeing. 2000 paper. This one's a rectangle. They told us A was W. We were also told OC is twice the length of OA. O is omega. So what is C is the first question. How can I get, the only one I know about is W at this stage. How can I get from A to C? Say that again.
Times it by 2 and times it by I.
Yeah, very good. Times it by 2, because the length of the vector is going to double, because we're told its length is twice. Times it by I, because we're rotating 90 degrees. So the vector OC, which in this case is the same as the point C, because we're joining it to the origin, will be the vector OA times 2I. So OC is the point C, OA is W, so C would just be whatever 2I times omega is. Second part of the question. What complex number corresponds to the point of intersection of the diagonals OB and AC? Okay, let's draw it. We know diagonals in a rectangle bisect. So D, therefore, must be the midpoint of AC. It's also the midpoint of OB, but that's not going to help me because I don't know what B is yet. But I do know A and C, and I know the diagonals bisect each other. So I've just got to find the midpoint of AC. So no, what is the midpoint? It's the average of the 2 points. So it'll be A plus C divided by 2. So the point A, whatever coordinates A has, whatever coordinate C has, divided by 2. So it'll be omega or W plus 2iw divided by 2. And so there's D. Half plus I times whatever W is. Okay, another example. OBA is an equilateral triangle. To make life easier for ourselves, they told us length is 1 unit. OBCD is a square, and obviously it also has length 1 unit because one of its sides is the same as the equilateral triangle. We want to find B, D, and C. Now, question like this. When they ask to find B, D, and C, the first thing I think of is, that's strange. Why didn't they ask to find B, C, and D? Why did they say B, D, and C? They're giving me a little hint here. Find D before you find C. Otherwise, why would they have said that order? It's not normal. So, okay. All right, let's find B. So I'm saying if I want to get the vector OB, it would be the vector OA, equilateral triangle. It'll be rotation 60 degrees. Length's not going to change because we said the length of that was 1. So we'll multiply by 1. So B is 1 times the cis of pi on 3, 60 degrees, half plus root 3 on 2i. So there's B. Now we have to get to C or D. The hint was D. Going to be a lot easier to find D because now I'm just rotating 90 degrees. So OD is equal to OB times I. D is equal to IB. We just worked out what B is. So now I know what D is. Now to get C, I could just add D to B because I can slide this vector up. So I can say, well, C will equal the point B, and I'm going to add on the vector OD. But the vector OD is just D because it's joined to the origin. And adding these two together, there's my point C. So it's all about playing with geometry. It's lots of fun. Okay. There's our wonderful diagram. I actually think this question came from a Catholic paper many, many years ago. But anyway, that doesn't matter. Part 1 and part 3, because part 2 was just boring, I think. Explain why P corresponds to this number. 1 plus I times Z1. Explain why. Well, hang on, what do we know? If I want to get P, how am I going to get P? I could get the vector AO, but be careful, I'm not rotating anti-clockwise, sorry. I've got to rotate clockwise to get P. So I'm actually multiplying it by negative I. Another way of thinking about that is I'm multiplying by cis minus pi on 2 because I'm adding negative pi on 2 to the angle. So I'm going back the other way. All right, so P minus A will be minus 1 O minus A. Playing around with that, we get to show, yep, there it is. That's why we end up with the 1 plus I times Z1. M is the midpoint of PQ. What complex number represents M or corresponds to M? Possibly that's what part 2 was. Find the coordinates of Q. Because we're going to have to do that. So there we go. Let's pretend that's part 2. The missing part there. So if I want to find Q, I'm going to have to do a similar thing. This time I'm rotating anti-clockwise. So that's just multiplied by I. So I'm getting OB rotating it anti-clockwise to get BQ. So, or QB, sorry. Or BQ. I've written it the wrong way around. I've said QB there. That should be BQ, shouldn't it? Fix that up on your sheet. That should be BQ, not QB. So head minus tail, I did that bit right. That is head minus tail. So Q minus B is I times negative B. And we get, there, we get 1 minus I Z2. So now we can find our midpoint because the midpoint is just the middle of 2 points. So part 3, it'll be whatever P is plus whatever Q is divided by 2. Sub in what we know. Make it look pretty. There we go. This time I've made it real and imaginary. It looks nice. Okay. So we've got 1E in the Cambridge. I've put in the Terry Lee exercise there because that's good as well.